formula for estimating the kilowatt size of an alternator based on the total kVA load is as follows: kilowatt size of alternator equals 120% times total kVA load. This formula generally assumes a power factor of 0.8, which is commonly used for typical electrical loads. Power factor is a measure of the ratio of real power measured in kilowatts to apparent power measured in kVA. A power factor of 1 indicates that all apparent power is being used as real power. The 120% factor provides a safety margin to account for unforeseen load increases, voltage drops, and other factors that can affect the alternator's performance. For example, if you have a total kVA load of 100 kVA, the estimated kilowatt size of the alternator would be kilowatt size equals 120% times 100 kVA, which equals 120 kilowatts. Consider the following. Firstly, the actual power factor. If you know the actual power factor of your load, you can use the following formula: kilowatt size equals total kVA load divided by power factor. Secondly, single phase versus three-phase. The formula applies to both single-phase and three-phase systems. However, for three-phase systems, you need to consider the phase voltage rating. Thirdly, surge loads. If your load includes motor starting or other high surge loads, you may need to increase the safety margin accordingly. Overall, the formula is a good starting point for estimating the kilowatt size of an alternator. By considering the actual power factor and other factors, you can refine the estimate for a more accurate selection. To elaborate further, let's delve into the specifics of power factor and its impact on alternator sizing. A lower power factor means that a larger alternator is needed to supply the same amount of real power. This is because the alternator must also supply reactive power, which does not contribute to the actual work being done but is necessary for the operation of inductive loads like motors and transformers. Therefore, if your load has a significantly lower power factor than 0.8, using the adjusted formula kilowatt size equals total kVA load divided by power factor will give you a more accurate estimate of the required alternator size. Understanding the difference between apparent power, real power, and reactive power is crucial. Apparent power, measured in kVA, is the total power that the alternator must supply. Real power, measured in kilowatts, is the power that performs actual work. Reactive power, measured in kVAR, is the power that is stored and released by inductive and capacitive loads. The relationship between these three is defined by the power triangle, where apparent power is the hypotenuse, real power is the adjacent side, and reactive power is the opposite side. The power factor is the cosine of the angle between the real power and the apparent power. When selecting an alternator, it is also vital to consider the altitude and ambient temperature of the installation site. Alternators are typically rated for operation at specific altitudes and temperatures. As altitude increases, the air becomes less dense, which reduces the alternator's cooling capacity. Similarly, higher ambient temperatures can also reduce the alternator's output. To compensate for these factors, it may be necessary to derate the alternator's kilowatt rating. Derating involves reducing the alternator's rated output to ensure that it operates within its safe operating limits. The amount of derating required depends on the altitude and temperature conditions at the installation site. Manufacturers typically provide derating curves or tables that specify the percentage of derating required for different conditions. Another important consideration is the type of load that the alternator will be supplying. Different types of loads have different characteristics that can affect the alternator's performance. For example, motor starting loads can draw a large amount of current for a short period, which can cause voltage dips and other problems. To handle motor starting loads, it may be necessary to use an alternator with a larger kilowatt rating or to use a soft starter to reduce the inrush current. Nonlinear loads, such as electronic devices and fluorescent lighting, can generate harmonic currents that can distort the voltage waveform and cause overheating in the alternator. To mitigate the effects of harmonic currents, it may be necessary to use harmonic filters or to select an alternator that is specifically designed to handle nonlinear loads. The alternator's voltage regulation capability is also an important factor to consider. Voltage regulation refers to the alternator's ability to maintain a stable output voltage under varying load conditions. A good alternator should have a voltage regulation of plus or minus 1% or better. This means that the output voltage will not vary by more than 1% from its nominal value, even when the load changes significantly. The type of excitation system used in the alternator can also affect its performance. There are two main types of excitation systems: static excitation and rotating excitation. Static excitation systems use electronic components to control the alternator's field current, while rotating excitation systems use a separate exciter generator to supply the field current. Static excitation systems are generally more efficient and reliable than rotating excitation systems. The alternator's cooling system is another important factor to consider. Alternators generate heat as they operate, and this heat must be dissipated to prevent overheating. There are two main types of cooling systems: air cooling and water cooling. Air-cooled alternators use fans to circulate air over the alternator's components, while water-cooled alternators use a liquid coolant to absorb heat. Water-cooled alternators are generally more efficient at removing heat than air-cooled alternators, but they are also more complex and expensive. The alternator's control system is responsible for controlling the alternator's operation and protecting it from damage. The control system typically includes features such as overvoltage protection, undervoltage protection, overcurrent protection, and short-circuit protection. The control system may also include features such as automatic voltage regulation, automatic frequency control, and load sharing. When selecting an alternator, it is important to consider the maintenance requirements. Alternators require regular maintenance to ensure that they operate reliably and efficiently. Maintenance tasks typically include cleaning the alternator, checking the bearings, and inspecting the windings. It is also important to have a qualified technician perform periodic inspections and repairs. The alternator's efficiency is another important factor to consider. Efficiency refers to the percentage of input power that is converted into output power. A more efficient alternator will use less fuel and produce less heat. Alternator efficiency typically ranges from 80% to 95%. When estimating the kilowatt size of an alternator, it is also important to consider the future load growth. If you anticipate that your load will increase in the future, it is a good idea to select an alternator that is larger than your current needs. This will allow you to accommodate future load growth without having to replace the alternator. Finally, it is always a good idea to consult with a qualified electrical engineer or alternator supplier to ensure that you select the right alternator for your application. They can help you to assess your load requirements, consider all of the relevant factors, and recommend an alternator that will meet your needs. In summary, calculating the kilowatt size of an alternator from the kVA load requires careful consideration of various factors beyond the simple 120% rule. While that rule provides a good starting point, a thorough understanding of power factor, environmental conditions, load types, voltage regulation, excitation systems, cooling systems, control systems, maintenance requirements, efficiency, and future load growth is essential for selecting the optimal alternator for a specific application. Remember, the formula kilowatt size equals total kVA load divided by power factor offers a more precise estimation when the actual power factor is known. Always prioritize safety and consult with professionals to ensure a reliable and efficient power generation system. Furthermore, let's discuss the impact of harmonic distortion on alternator sizing and performance. Harmonic distortion refers to the presence of harmonic frequencies in the voltage and current waveforms. These harmonics are caused by nonlinear loads such as variable frequency drives, electronic ballasts, and uninterruptible power supplies. Harmonic currents can cause several problems for alternators, including overheating, increased losses, and reduced lifespan. Harmonic voltages can also cause problems for sensitive electronic equipment. To mitigate the effects of harmonic distortion, it may be necessary to use harmonic filters or to select an alternator that is specifically designed to handle nonlinear loads. Harmonic filters are devices that are installed in the electrical system to reduce the amplitude of harmonic currents and voltages. There are two main types of harmonic filters: passive filters and active filters. Passive filters use inductors and capacitors to create a low impedance path for harmonic currents. Active filters use electronic components to inject harmonic currents into the electrical system that are equal in magnitude but opposite in phase to the harmonic currents produced by the nonlinear loads. Active filters are generally more effective than passive filters at reducing harmonic distortion, but they are also more complex and expensive. When selecting an alternator for an application with significant harmonic distortion, it is important to choose an alternator that is designed to handle nonlinear loads. These alternators typically have reinforced windings and improved cooling systems to withstand the effects of harmonic currents. They may also have harmonic filters built into the alternator control system. Another important consideration is the alternator's transient response. Transient response refers to the alternator's ability to respond to sudden changes in load. A good alternator should have a fast transient response, which means that it can quickly restore the voltage and frequency to their nominal values after a sudden load change. The alternator's transient response is affected by several factors, including the alternator's inertia, the excitation system, and the control system. Alternators with higher inertia tend to have slower transient responses. Static excitation systems generally provide faster transient responses than rotating excitation systems. Sophisticated control systems can also improve the alternator's transient response. When selecting an alternator for an application with frequent load changes, it is important to choose an alternator with a fast transient response. This will help to ensure that the voltage and frequency remain stable even during sudden load changes. In addition to the factors discussed above, it is also important to consider the alternator's environmental protection. The alternator should be protected from dust, moisture, and other contaminants that could damage its components. The level of environmental protection required depends on the installation environment. Alternators that are installed outdoors typically require a higher level of environmental protection than alternators that are installed indoors. The International Protection Marking System, or IP code, is an international standard that classifies the degree of protection provided by electrical enclosures. The IP code consists of 2 digits. The first digit indicates the level of protection against solid objects, and the second digit indicates the level of protection against liquids. For example, an alternator with an I54 rating is protected against dust and splashing water. Finally, it is important to consider the alternator's warranty. A good alternator should come with a comprehensive warranty that covers defects in materials and workmanship. The warranty should also cover the cost of repairs and replacements. Before purchasing an alternator, be sure to carefully review the warranty terms and conditions. In conclusion, selecting the right alternator involves a comprehensive understanding of various factors, including load characteristics, environmental conditions, and performance requirements. The 120% rule provides a basic estimate, but a detailed analysis of power factor, harmonic distortion, transient response, environmental protection, and warranty is crucial for ensuring a reliable and efficient power generation system. Always consult with qualified professionals to make an informed decision and ensure the long-term performance of your alternator. Let us add another layer to our discussion by considering the economic aspects of alternator sizing. Oversizing an alternator can lead to higher initial costs, increased fuel consumption, and reduced efficiency, especially when operating at light loads. On the other hand, undersizing an alternator can result in overload conditions, voltage instability, and potential damage to the alternator and connected equipment. Therefore, finding the optimal balance between initial cost and operational efficiency is crucial. A life cycle cost analysis can be a valuable tool for evaluating the long-term economic implications of different alternator sizes. This analysis takes into account factors such as initial cost, fuel consumption, maintenance costs, and replacement costs over the expected lifespan of the alternator. By comparing the life cycle costs of different alternator sizes, you can make a more informed decision about which alternator is the most cost-effective for your application. Furthermore, consider the impact of renewable energy sources on alternator sizing. In many applications, alternators are used in conjunction with renewable energy sources such as solar and wind power. In these hybrid power systems, the alternator serves as a backup power source when the renewable energy sources are not available. When sizing an alternator for a hybrid power system, it is important to consider the variability of the renewable energy sources. The alternator should be sized to handle the peak load demand when the renewable energy sources are producing minimal power. It is also important to consider the interaction between the alternator and the renewable energy sources. The control system should be designed to seamlessly switch between the renewable energy sources and the alternator and to optimize the overall system efficiency. Another important aspect to consider is the paralleling of alternators. Paralleling refers to the operation of two or more alternators in parallel to supply a common load. Paralleling can provide several benefits, including increased reliability, improved efficiency, and greater flexibility. When paralleling alternators, it is important to ensure that they are properly synchronized. Synchronization involves matching the voltage, frequency, and phase angle of the alternators before connecting them in parallel. Improper synchronization can result in large circulating currents, which can damage the alternators. Sophisticated control systems are available that can automatically synchronize alternators. In addition to synchronization, it is also important to consider the load sharing between parallel alternators. Load sharing refers to the distribution of the load among the alternators. Ideally, the load should be shared equally among the alternators to maximize efficiency and minimize stress on the individual alternators. Load sharing can be achieved through various control strategies such as droop control and isochronous control. Droop control involves setting the frequency of each alternator to decrease slightly as the load increases. Isochronous control involves maintaining the frequency of all alternators at a constant value, regardless of the load. Both droop control and isochronous control have their advantages and disadvantages, and the best control strategy depends on the specific application. In addition to the technical and economic considerations discussed above, it is also important to consider the regulatory requirements that may apply to alternator installations. These requirements may include codes and standards related to safety, emissions, and noise. It is important to comply with all applicable regulatory requirements to ensure a safe and environmentally responsible installation. Consulting with local authorities and industry experts can help to ensure compliance with all relevant regulations. To summarize, alternator sizing is a complex process that requires careful consideration of various factors. While the 120% rule provides a useful starting point, a thorough understanding of load characteristics, environmental conditions, performance requirements, economic considerations, renewable energy integration, paralleling techniques, and regulatory requirements is essential for selecting the optimal alternator for a specific application. Always consult with qualified professionals to make an informed decision and ensure the long-term performance and reliability of your power generation system.